For homework 1, part B, we're going to be deriving two equations for both the temperature change and the change in concentration within our CSTR at steady state. So the first thing we need to know for that is that our concentration of A, or not our concentration or A, however the total amount of A in our tank is equal to the volume times the concentration of A. Therefore, the change in the volume concentration of A with respect to time is going to be equal to our Qin times our CAin minus our Q out times our CA out. So next we need to know that when we look at this left side of the equation, that we can use the product rule to separate these two different variables within our derivative. So we have our volume times the change in concentration with respect to time plus the concentration times our change in volume with respect to time. And that is equal to our right side still. And we know from part 1 of this homework that our dV over dt is equal to our cross-sectional area times our dH dt times CA. So that is now the left side of our equation, which is still equal to the right side. And now we're going to use some of our steady state assumptions. Steady state. And the fact that this CSTR is well mixed. Because the CSTR is well mixed, we can assume that our concentration out is equal to the concentration of the tank. And because we're at steady state, we know that Q in equals Q out, so these will both just be Q. And lastly, because we're at steady state, our dH dt is equal to 0. So all of this is turned to 0, leaving us with just our volume times our dCA over dt is equal to what we have up here. So we'll rewrite that. dCA over dt is equal to RQ times CAN minus Q times CA. So then all we need to do is we can pull out this Q, leaving us and divide across by V, giving us our dCA over dt is equal to Q over V times our concentration going in minus the concentration of the tank, or what's going out. And then the last thing we have to remember to get our final change in concentration is that there will be an exothermic reaction happening within the CSTR, meaning that our total change in concentration will also have to take into account the amount of Ca that is reacting using K, or our reaction rate. So this will be the final equation for how we will calculate the change in concentration of our CSTR at steady state that is well mixed. Next, we will use the energy balance of the system in order to determine the rate at which the temperature is changing. So our overall energy equation can be represented as our change in our density times our volume times heat capacity times temperature, all with respect to time. And this part will be equal to our flow rate coming in and our flow rate going out, which we've already established is just Q, times our heat capacity times the density times the temperature coming in, which will be changing, minus flow rate out, which again is the same, heat capacity, density, temperature out. Then another thing we need to account for in this is our reaction taking place. So this will be adding energy to our system. So we will be plus our heat of reaction, negative heat of reaction, times the rate at which it's occurring at, which is going to be our concentration, times K, times our total volume. So this is our reaction. And then lastly, we'll have the heat transfer going to the jacket outside. So our heat transfer, this is going to be minus because this will be taking energy away from our system, which will be equal to our heat transfer coefficient times the temperature of our system minus the temperature of the cooling water. So now we can put this all into one big equation, but it's also important to note that our density, volume, and specific heat coefficient, they're all going to be constants, so these can be pulled out, giving us rho VC times dt, capital T, with respect to time, will be equal to our Q C density T in minus Q C density T out, which, because it's at steady state and well mixed, this T out is just going to be T. And then we will have plus our negative heat of reaction times CAK times our volume, and then minus heat transfer coefficient times the difference in temperature between our system and the cooling jacket. So now what we can do is we can divide across by rho VC. So if we just look, we get our C and rho canceled out here, leaving us over V. What can we, oh. So we'll also be able to pull out this Q, just leaving us with, cross this out, we have our T in minus T, and then our C and rho cancel out, so we're just left with the Q we pulled out and our volume. So we have Q over V times difference in temperature, and then plus heat of reaction times CAKV. So we only get rid of V here, leaving us over rho C, and here we have nothing to cancel out, so we have over rho VC. So that leaves us with dt with respect to time is equal to Q over V, temperature coming in, minus the temperature of our system, plus the negative heat of reaction multiplied by concentration, K, volume, oh, we got rid of volume, just K, over rho C. Lastly, minus heat transfer coefficient times our temperature minus temperature of the cooling water. That's all over rho VC. And this is how we will calculate the change in temperature in our well-mixed steady state CSTR. Continuing homework 1, part B, we'll be using the equations we derived in the previous part to create a function at which we'll be able to use solve IVP in order to, or we'll be able to create a function that is an initial value problem, which we'll be able to use solve IVP in order to determine how our system is changing with time and the changing concentrations and temperatures within our well-mixed steady-state reactor. So the other things we have here are all of our givens from the problem statement, which we'll be using in our equations, and then we'll be running this simulation for 10 minutes, which is our t end. So we'll start by defining our function. We'll call it right-hand side, which will be time, and then our vector, which we will unpack our vector into concentration and temperature. It's important to note that the k we are given in the problem statement is our k0, which this is not a constant and is dependent on our temperature. With more heat, it will react faster, and with less heat, it will react slower. So our k that we'll use in our calculations is equal to k0 times exponential of our negative ER over our temperature, which will be changing. And the next thing will be our change in concentration with respect to time will be equal to our flow rate divided by our volume. Flow rate divided by volume times our initial concentration, CAI, minus our current concentration, CA. And then from this, we will subtract our K, which we just calculated, times the concentration, which is representative of the concentration of A that is reacting. So next, we have our change in temperature with respect to time, which is equal to our flow rate divided by volume again, multiplied by our initial temperature minus the current temperature. To this, we will add our negative heat of reaction, so negative HR multiplied by K multiplied by our concentration. This is then divided by rho multiplied by C. And finally, we'll subtract our heat transfer coefficient multiplied by our current temperature minus the temperature of the cooling water, and this will be divided by rho times C times V. Take a look quickly, see if we're missing anything. I guess we can double check the equation we just derived. So Q over V, T minus Tn, negative heat of reaction, CAK over rho C, UA, T minus TC, rho VC. So rho VC, rho C, UA, T, TC. So that all looks good. And from this, we will return both dCA, dt, and dt. Alright, so next we'll use solve IVP, give it our initial guesses, and then that should solve for each time step, and from that we'll be able to plot our results. So our result is going to be equal to solve IVP of our right hand side from 0 to our t end. Our initial guesses for CA and T will be CA0 and T0. Method will be rad U, and our dense output is equal to true, so we can evaluate it at each individual time. Float is not an object. What happened? So it seems I have just forgot to multiply our UA, which is unfortunate. Alright, so that seems to work now. So we can now create our t-plot. So our time for plotting is going to be equal to NP linspace from 0 to our t end. We'll have 100 points. And then our CA plot is going to be equal to our res.saw of our t-plot, so evaluated at each individual time. Because we have both CA and T in our solution, we need to take the first value, which is CA, because that is the first one we return, and then our temperature for plotting will be equal to res.saw of our t-plot, and this will be the second value. So then we just need to plot these things. So our figure will be to make subplots. We will have our rows equal to 1 and our columns equal to 2. So now fig.add scatter. Our x is going to be our t-plot. Our y will be our CA plot. This will be in row 1 and column 1. And the name for this is going to be concentration. And then copy this. So now we want, for our y, we want it to be our temperature plot, and then column 2, and then this will be our temperature. So as you can see, when it first starts, we start at our initial concentration of 0.5 and our initial temperature of 350. And because the concentration is so high, it begins to react very quickly, which then in turn very quickly spikes the rate at which it reacts, generating a lot of heat. And this heat increases the rate of reaction further, driving the concentration all the way down to 0, where it is no longer able to react and generate heat because the concentration is so low. This causes the heat to end up dropping and the concentration to accumulate and build up again. And once it reaches a point to where the concentration is high enough again, it begins to shoot up and generate heat, in turn causing it to react faster and bring the concentration lower. And this cycle continues almost indefinitely. Okay.